Live now. Okay. Okay. Hi, everyone. Thank you so much for joining this webinar today. My name is Allie Yamagata. I'm the YPN Semester Division Liaison. Here's the agenda for some of like the next webinars we're gonna have. And before we start this webinar, I would like to talk a little bit about ACerS members' benefits. And so the ACerS memberships give you access to a lot of resources that allow you to continue to learn and grow, gain recognition with awards and scholarships, for support to travel and attend conferences. And here are some of our benefits. And here's just like our membership path that you can like, it changes the cost of like the membership depending on where you are in career. For students, it's like, for example, it's for $30. For graduate students, also $30. And after you graduated or if you're already like working, you can get like an associate membership, which the first year is for free. And the second year will be $40. So you can like, get to know us without like having a lot of costs. And then like the individual membership, it would be $120. I would like to shout out that there's still like 2 days. You have until Friday to sign up for the mentorship programs for ACerS. This is a really like nice opportunity. I already went through this program and it's really great to connect with someone. So there's like different programs for students, faculty, and industry. It's really like nice because you're going to be connected to someone, like if you're depending on if you're a student, would be like someone that could mentor you. It's a faculty, a senior faculty could like be matched with your industry, someone like your industry, but it would be a person that doesn't work with you. So it's a very interesting like to make this relationship and they can help you grow your career. So yeah, there's still only like 2 days, guys. You can join ACerS today and still sign up for like the program. I also gonna like talk a little bit of the Cement Division, which is hosting this webinar. So the Cement Division is one of the 11 divisions for the in the American Ceramic Society. We advance the fundamental material science of cement, we fancy on nano to micro scale research, and develop new technologies for concrete. There is a lot to do in here. You can connect with industry professionals, come to meetings, symposium, and related events to stay current, access to member resource and industry publications, their leadership development opportunities, and awards and recognitions, and access to peer-reviewed journals. So we host an annual like meeting, which is the Advanced in Cement-Based Materials meeting, which is a science-based meeting focused on the world most used construction material. It's a unique event for cement chemists. There is a research showcase in presentations and poster sessions, and you can network with professionals for academia, industry, and research labs. There's also opportunity for students to get like travel support and also participate in actually organizing those events. You can sign up today, and if you want more information, you can contact like Vicki Evans through this email. And I would like to ask you guys to save the date for the next meeting that's going to happen in the University of Colorado Boulder on June 11, 13. And we're going to keep you posted for like more stuff. I want to like remind you guys on February, we already have a couple of scheduled Driving Star webinars, and we're going to send an invitation for you guys after this this webinar. I would like now to give the floor for our speaker, Professor Chengcheng, who's gonna like talk right now. So Dr. Chengcheng is an assistant professor in the School of Construction Management Technology at Purdue University. She got her PhD degree in civil engineer from the University of Florida. Before joining Purdue, Chengcheng worked as an Rice postdoctoral research fellow at DOE National Energy Technology Laboratory Chengcheng's research interests include cement modeling optimization, cement rheology, computational mechanics of materials, and machine learning applications. She has received support from federal, state, and private sources such as ACI, USDOT, and NSF. So thank you so much, Chengcheng, for joining us today, and we're really excited to have you. I'll give you the floor to you now. Thank you.
Thank you, Allie, for the introduction. I'm going to share my screen. Can you see?
Yeah, we can see it. Yeah,
Oh, yeah. Can you see my screen?
Yeah, I can see your screen.
Like which? Can you see the full screen?
Yes. Yeah,
okay.
we can. Yeah.
Okay. Hi, everyone. Good afternoon, everyone. My name is Chengcheng. I'm an assistant professor in the School of Construction Management Technology at Purdue University. It's my great honor to give the presentation today at the ACerS Cement Division Rising Star webinar. I'm going to talk my research on the computer-aided sustainable cement manufacturing and materials with modeling, virtual design, and optimization. So here is the outline of my presentation. First, I'm going to introduce the motivation of my research, and then I'm going to talk about two research projects. One is on the optimization of cement manufacturing and hydration for enhanced performance and sustainability. The other one is rheological behavior of the oilwell cement slurries using the rheology modeling. And then the last one is concluding remarks. First, motivation. First, let's see the metrics of the cement and concrete industry. Cement and concrete industry are the most widely used like cement and concrete are most widely used construction materials in the world, and the production process is energy and carbon intensive. So in 2023, the U.S. cement production is about 91 million metric tons, and the ready-mix concrete production is 393 millions of cubic yards. And this industry is responsible for 1,600 megatons per year of the CO2 emissions, which is about 8% of the global emissions. And half of the emissions comes from the calcination of the limestone, and the other half comes from the burning of the fossil energies in the cement kiln production process. So if we assume CO2 emissions from concrete is a single country, it ranks number 3, as you can see here, like compared to all of the countries in the world. Not only the CO2 emissions is a challenge, the energy consumption in this industry is also a big issue. It consumes about 11% of the energy among all the industries. In order to make the cement industry more sustainable and achieve the carbon neutral goal in the future, we need to reduce the greenhouse gas emissions and reduce the energy consumption while maintaining the performance of the materials. So here is my research objective. In order to address those challenges, my research objective is to develop a computational efficient framework by integrating different model components, such as the material models, like the cement hydration model, cement rheology model, and the physical chemical models for the clinker production, the multi-objective optimization, and the machine learning algorithms. Through the comprehensive computational framework, we could get a reliable, high-performance, sustainable, and cost-effective material and manufacturing design. So the first project I'm going to talk is the optimization of cement manufacturing and hydration for enhanced performance and sustainability. So this is a project funded by Florida DOT when I was working on my PhD degree. So for this project, I have several goals. The first is I want to reduce the energy consumption and CO2 emissions during the cement manufacturing process. Second, I hope to extend the working life of the raw feed quarry by optimally balancing raw materials and conducting eco-friendly and cost-effective practice. I also want to optimize the cement and concrete design process by reliably and efficiently predicting the material properties. So in order to achieve these goals, we want to look at the whole process from the cement clinker production, cement hydration, and the process optimization. Physical testing to investigate this process is very time-consuming and costly. So I came up with a multivariant computational framework to optimally simulate the cement manufacturing process, cement hydration process, and the concrete mixing process. So here is the overview of the framework. It consists of 3 components. First is the VCP, it's short for virtual cement plant. It simulates the chemical reactions and thermodynamics inside the cement kiln. Second is called VCCTL. It's short for Virtual Cement Concrete Testing Lab. It's a software that can be used to simulate the cement hydration process and predict the properties for the final products. And third is optimization and machine learning applications on the integrated VCP and VCCTL models to increase the computational efficiency. So here are the 3 model components. Let's look at them one by one. The first one is VCP. So virtual cement plant model is a physical chemical model to simulate the chemical reactions and heat transfer process inside the cement rotary kiln. So now let's see what happened inside the cement kiln. There are several major chemical reactions going on from the calcination of the limestone. So from these chemical reactions, we can get different cement phases like A-light, B-light, aluminate, ferrite, as well as the carbon dioxide from the calcination of the limestone. So the cement clinkers consist of those phases. In addition, temperature is also one of the most important factors that determine the production rate of the cement, and it is also related to the energy consumption. So I simulated the heat transfer process, including the conduction, convection, and radiation process inside the kiln. And here I listed the major mathematical equations to simulate the chemical reactions and heat transfer process in the kiln. From the coupled material balance equations and thermodynamics balance equations, I got the mass fraction of different cement phases and CO2 emissions. I could also get the temperature changes inside the kiln. So this virtual cement plant model has a large flexibility with more than 50 parameters, which could be designed and customized according to user requirement. Like we can easily change the geometry of the kiln, we can easily change the initial temperature conditions, and also change the location of the burners using this model. So here is a demonstration of the virtual cement plant simulation result. The top 2 animation, the top 2 figures shows how the mass fraction of the cement clinkers generated inside the kiln. And the bottom 2 figures shows how the temperature profiles for gas, for the kiln wall, and for the cement solid changes inside the kiln. We could see that the 3 temperature becomes uniform after the heat transfer process finishes. Compared with the physical testing, the VCP model has much more flexibility. It can simulate the cement plant with different conditions, different geometries, different raw feed proportions, and different temperature conditions. So in this way, VCP has broader applications for not only the cement industry, but also other high temperature material manufacturing industry. It can be used to improve the material production and improve the performance and sustainability of the material manufacturing process. I also validated my simulation result with some published industrial kiln data. As we can see here, the VCP model result have a good match with the data from the industry with a very small residues here. The second part, the second model component is called VCCTL. It's short for Virtual Cement Concrete Testing Lab. It simulates the cement hydration process and predicts the material properties for cement and concrete. So the VCCTL is a software developed by NIST. It simulates the cement hydration process and predicts the chemical and mechanical properties for cement and concrete, such as the modulus for 7 days and 28 days, heat of hydration, and compressive strength. The pictures on the right shows the three-dimensional microstructure recreation from two-dimensional cement phase inside the VCCTL. So although VCCTL is a mature software developed for a long time, my research group at the University of Florida conducted some physical tests to validate the VCCTL, and the result turns out very good. So here is the user interface of the VCCTL. You can define the parameters as you need, such as the cement phases information and the temperature conditions, and then you click the Run button to start a simulation. So since the hydration is a very complicated process, there are a lot of parameters in the model. So in order to achieve the optimal material design goal, I need to get a larger data set from a bunch of simulations. So if I change the parameters one by one using the user interface, it's very time consuming. It takes about 2 hours for each run. So we put the simulation on the high performance computing cluster at the University of Florida, which is called HyperGator. So on the right, it shows the Linux interface running the VCCTL on the HPC cluster. We could submit thousands of simulation jobs at one time. So here is VCCTL enumeration for large data set running on HPC. So in the table, I listed the input for VCCTL. I gave a reasonable range for each input and generate about 150,000 unique combination for VCCTL to run. It is a huge amount of data. If we run these combinations with VCCTL user interface, it may take about like 20 CPU years to finish. But with the help of HPC, the computational efficiency is increased dramatically. The simulation can be done in 3 weeks. And the third part is the optimization part. So in order to further improve the efficiency and find the optimal solutions, I applied some AI-based meter-heuristic optimization algorithm and machine learning techniques on the integrated model. So with these techniques, I'm able to optimize the cement material design and cement manufacturing process for better performance and sustainability. So here is the potential discrete combinations about the data set. Both VCP and VCCTL models are full of parameters, including different cement phases, concrete aggregates, and the operational conditions inside the kiln. With the increase of the input, the combination, the total number of combination will be increased exponentially. So for my study, I selected 8 input, including the 7 cement phases and 1 water to cement ratio parameter. So we can see that the total number of combination is about 10 to 5 different simulations. So we definitely need some smart searching algorithm to improve the efficiency and find the optimal solutions according to the user requirement. Meta-heuristic optimization is a great approach that is suitable for the discrete problems. For my research, I applied 2 meta-heuristic algorithms. One is called particle swarm optimization, that is inspired by the nature animals like bees or fishes, how they search for food. And the other one is called genetic algorithm. It's inspired by the natural selection process. Today, I'm going to talk about the PSO algorithm. So basically, the particle swarm optimization algorithm simulates the idea of a group of animals like bees to catch the target like flowers or food. This algorithm is a population-based method, not gradient-based. So it does not require the problem to be differentiable. We don't need the equations for the optimization. It can search very large database and it allows for more freedom and less sensitivities on the objective functions. So here is the flow chart of the particle swarm algorithm. The movement of the particles are guided by two best positions. One is called the local best. Local best means the best position of that particle has achieved so far. The other one is called global best. It means the best position inside the entire swarm. By updating the velocities and positions of the particle every iteration, we could find the optimal solutions according to the objective functions. So now let's see how the algorithm works. I often explain this particle swarm algorithm using an example of a group of minions trying to find bananas. So here, the first step, all minions don't know the position of the banana. Banana is the objective function, so they have to conduct the blind search everywhere. After the first step, we have 4 minions who have the best performance compared with themselves. They are the local best. And among the 4 minions, we have one superstar. His name is Kevin. He has the best performance in the entire minion group. He is the global best. So Kevin will lead the search for the next iteration. Everyone will follow him and update their position and velocities iteration after iteration. With the lead of the local best and global best, the minion finally find the objectives, which are bananas. And here is a demonstration of the particle swarm application on the cement optimization. So here, this case is a single objective optimization case. Here I want to optimize the 7-day modulus to 15 gigapascal. We can see that after 40 iterations, the algorithm converges and the modulus hit the target. At the optimal solution, we could get the information of the cement phases. So this approach is meaningful for the cement industry. The industry could get the optimal solution, optimal proportion of the cement phases according to user requirements. They don't need to conduct many physical or virtual tests. So here I only demonstrated the modulus as the single objectives. But we all know that in our practical construction process, there are a lot of factors to be optimized at the same time, like the cost, the time, and the energy. So how could we optimize those parameters at the same time? So in order to solve for those problems with multiple objectives, let's first look at a more practical daily question. So like before we want to buy a car, we have two objectives to consider, comfort and cost. How do we make the decision? So I will introduce the idea of the Pareto front for this problem. The Pareto front provides the trade-off optimal solutions for decision makers. For example, if the buyer really care about the comfort of the car, they have to pay extra money, and if they want a low-cost car, they have to sacrifice some comfort. So the Pareto front analysis is a very useful tool for the multi-objective optimization problems. So in the next slides, I'm going to show the optimization result on multiple objectives for the integrated VCP and VCCTL models. So here are the case studies of the optimization with two objectives. Like the first figure here, we want to optimize the modulus and the setting time at the same time. So the colorful dot inside are the data set from the integrated VCP and VCCTL model simulation results. And we have different water to cement ratios and different cement phases and different cement operation conditions. And there are 4 Pareto front from the simulations from the particle swarm simulation result. The four Pareto front are shown with the red lines. So for the cement industry, we always want to maximize the modulus while minimize the setting time for faster construction. So the min-max Pareto front on the top left contain the information we want. Similarly, for the second and the third cases, we are optimizing the modulus versus cost and the modulus versus the CO2 emissions. So in order to build a green and low cost cement industry, we always want to minimize the greenhouse gas emissions and maximize the performance of the materials. Also, we want to minimize the cost as well. So in this way, we want to look at the min-max Pareto front on these two cases to achieve those optimal solutions. And in addition, the particle swarm algorithm search decreases the computational cost by more than 90% compared to the blind search from the big data. That means the particle swarm would complete the simulations in a few days rather than 3 weeks. So here is another case. Here we want to optimize the 3 objectives. In this case, we want to minimize the setting time, minimize the energy, and maximize the modulus at the same time. So the animation shows how the optimal solution was found by the particle swarm optimization algorithm. And since we have 3 objectives, the Pareto front becomes a 3-dimensional surface, combining all of the optimal solutions. And the right figure shows the 3-dimensional Pareto surface. We are interested in the right Pareto surface because it contains the information, it contains the optimal design for modulus, energy, and setting time for the cement industry. And here is another case for the 3 objective function optimization. Here we want to minimize the CO2 emissions, minimize the cost of raw materials, and maximize the modulus. So this Pareto front contains the optimal solutions. So from this information, from the simulation result, the information can be used to make the decisions based on the weight of the performance, economy, and sustainability. For example, if it's acceptable to sacrifice some strengths, like 18% reduction in modulus, then the sustainability and economic value will improve a lot, which is about 9% reduction in cost and 15% reduction in the CO2 emissions. So currently, cement industry does not have a tool like this that can optimize the entire cement manufacturing process and the cement hydration process and predict the final product properties. So the multi-objective optimization with Pareto front analysis on the integrated model provide a very powerful tool for the cement industry based on the user's requirement. According to the optimization result, I also developed a grading system ranging from 0 to 1 to evaluate the performance of the cement materials by considering multiple factors such as material property, energy consumption, and sustainability. So here is an example. From the figure on the left, the cement A has a relatively low score. We define it as 0.3. because it has high setting time and high energy consumption. If we modify cement A by reducing the A light and increasing the B light to produce the cement B, so we can see the score is increased to 0.85 because the energy consumption is reduced. For further improvement of the cement, we can reduce the water to cement ratio of cement B to produce cement C, and then the score becomes 0.99 because it decreased the setting time by 40%. So this grading system provides a practical and effective approach to rate the materials according to user requirement for the cement industry. So in order to further improve the computational efficiency for the modeling and optimization, I applied machine learning techniques to improve the simulation process. I developed a surrogate model for the whole process, from the raw material, cement clinker production, cement hydration, all the way to the final products. For example, I applied Gaussian process regression algorithm to train and test the dataset from the integrated VCP and VCCTL models, and the surrogate model works quite well with the larger dataset. So the AI-based optimization and machine learning techniques significantly increase the efficiency for the cement industry. For example, if we search optimal solutions by conducting physical tests, it requires about 28 days per test, which is about hundreds of years to finish. And if we apply the user interface of the virtual cement testing lab, it requires about 20 CPU years to finish the simulation. And if we run the simulation on high performance computing cluster with parallel computing, it takes about 3 weeks. And if we apply AI optimization and machine learning algorithm, we can find the optimal solutions based on user requirement within 2 or 3 days. So this computational framework significantly reduces the time and cost, and is also very user-friendly for the cement and concrete industry. So that is the first project, and then I'm going to talk about my second project. Is about the rheological modeling of oil well cement slurries. So this research is my postdoc research at the DOE National Energy Technology Lab. So first, let's see a picture of the deep water drilling explosion happened outside the coast of the Louisiana in 2010. The explosion caused a lot of injuries and deaths. So safety for the oil well cement industry is very important. According to the report after the accident, the explosion is caused by the cement failure, which is related to the gas migration process into the well-borne cement slurries. So in order to decrease the geotechnical risks, it's very important to understand the cement slurry rheology. So here is the background information about the well cementing. As shown in the diagram, the well cementing is the process of placing a cement slurry in the annular space between the well casing and the geological formation surrounding the well bore. The process is to provide zonal isolation in wells, and the hydrostatic pressure must exceed the formation pressure to prevent the gas migration process through the cement annulus. And the operation environment for the for the well cementing is challenging. For example, it could happen under high temperature, high pressure conditions. The geological formation may be very weak, and you may also find some corrosive fluids during the operation. So as a result, the gas migration into the well cement could be a serious problem before the cement slurry has developed the strength, and some permanent pathways can happen before the cement is placed. So my objective for this project is to understand the rheological property of the cement slurry in oil well applications, and understand the gas migration process in the hydrating cement to reduce the drilling risk. So that's why we need a comprehensive rheological model to simulate the cement slurries. So for this project, I simulate the behavior of oil well cement slurry as non-Newtonian fluids. So you can find non-Newtonian fluids in our daily life. Like the first one is ketchup. So the ketchup is kind of shear thinning fluids. The viscosity of ketchup decreases with the increase of shear rate. That means the ketchup stay almost solid in the bottle, in the bottom of a bottle. And when we start to squeeze the bottle and give some pressure on the ketchup, it could squirt out easily. The second one is the mixture of the cornstarch and water. It shows the shear thickening behavior. So when we push the mixture harder, it becomes more thicker and more viscous. The third one is the yogurt. Yogurt is a sextropic fluid. The viscosity decreases with the stress over time. So if we stir the yogurt at a constant rate for a while, you will find it becomes thinner and thinner. And the last one is printer ink. The printer ink is rheopactic fluid. So the printer ink will become thicker with the stress over time. And these two figures shows the commonly used mechanical models, rheological models for the non-Newtonian fluids. Like the Hershey-Berkeley model is the simplest, one of the simplest rheological model for non-Newtonian fluids. The model is in one-dimensional, and the n is the parameter that decide the shear thinning or shear thickening behavior of the fluids. So in order to reduce the risk, the drilling risk caused by the cement failure, I studied the behavior of cement slurry and modeled it as non-Newtonian fluids. I also look at some important parameters that affect the material behavior. So most of the published data, like the rheology model on the published papers, are in one-dimensional and only consider the single factors like shear rate. So I developed a comprehensive cement rheology model considering different factors like the volume fraction, the shear rate, the time-dependent sextropic behavior, the water-to-cement ratio, and time and pressure. So this model is in three-dimensional using the tensor notation. So here is a governing equation, the four basic governing equations in fluid mechanics. So I just substitute the constitutive models I developed to the governing equations and solve for the fluid behavior for the oil well cement slurries. After I developed the constitutive model and the governing equations, I did some case studies for steady flow and transition flow in channels and pipes. So here I just show one case with the steady flow of a cement slurry in an inclined channel. So here I simulate the cement slurry as non-Newtonian fluids and use my own constitutive models and solve for the velocity profile and the volume fraction profile. So from the parametric studies, the parameters such as the angle of inclination, the maximum packing fraction, and the pressure have significant effect on the velocity and the volume fraction profile. So here is the parametric study result. The slides show the effect of the inclination angle theta. As most drilling operations are done either in a vertical or horizontal arrangement. So I look at different cases. I change the theta from 0 degree all the way to 90 degree and see the effect of different inclination angles on the velocity and the volume fraction. So from the two figures on the right, the velocity shows a parabolic distribution and the particles tend to concentrate at the center. Larger values of theta result in faster flow. When the plates are inclined at a sharper angle from horizontal to vertical, the particles tend to move faster and have lower concentration at the plates. So here is another parametric study result by detecting the effect of the maximum packing fraction. It means the volume fraction at which the viscosity approaches infinity. As the Phi increases, the velocity tends to increase, and more particles tend to concentrate at the center. And from the figure on the right, we can see that both the velocity and the volume fraction distributions become more non-uniform for larger values of the maximum packing fraction, which indicate a higher packing. So after I studied the rheology of oil well cement slurries, I also want to look at the gas migration process in practice to reduce the drilling risks for oil and gas industry. So the animation on the left shows the gas injection process into the fluid with different velocities in the channel. And the right figure shows the validation, experimental validation by our collaborators at the University of Pittsburgh. They are using the well-born simulation chamber to validate my simulation results. And I also created a three-dimensional cylindrical geometry to simulate the cement slurry placement. The animation on the left shows the cement slurry placement process into the drilling fluids. And the animation on the right shows the gas migration process into the three-dimensional cement annulus using the ACerS Fluent software. And I'm integrating my comprehensive cement slurry model into ACerS by creating user-defined function for the constitutive laws. And the CFD simulation result for multi-phase flow will efficiently guide the design for the oil well cement industry. So this is a summary of this research project. In conclusion, gas migration is a serious problem in well cementing. Understanding the rheology of oil well cement is very important for us to reduce the drilling risks in the well cementing. After we reviewed the models, rheology models, we found that most of the models are in one-dimensional and only consider single factors in the model. So we came up with a comprehensive rheological model for the oil well cement slurries in 3 dimensions, considering different factors like shear rate, volume fraction, water to cement ratio, cyclotropic behavior, and so on. And we also simulated the steady flow of cement slurry and performed parametric studies to see the influence of different parameters on the cement behavior, and simulate the gas migration process using CFD software. So the research can be used to guide the design for the oil well cement industry and reduce the drilling risk in the future. So in conclusion, my research is about the technology to increase sustainability of cement and concrete industry with improved performance, lower carbon footprint, lower energy consumption, and lower cost. I developed the computational framework that applies cyber-physical research to reduce the reliance on physical testing and open new pathways to improve computational analysis. I also applied artificial intelligence approaches, including the multi-objective optimization and machine learning algorithms for the integrated material and manufacturing models, and developed a tool to characterize and evaluate the materials and manufacturing process by improving the sustainability for the cement industry. So that's all my presentation, and I would like to thank the funding support, the funding from FDOT, NETL, AllRise, NSF, ACI, Illinois, Indiana Sea Grant, and also want to thank my colleagues and collaborators at Purdue University, University of Florida, and the National Energy Technology Lab. Here is my reference for this presentation, and thank you very much for your attention, and I'm open to any questions.
Yeah, hello everyone. Thank you so much, Chengcheng, for your presentation. That was very impressive and amazing. People can send questions on the Q&A session, the chat. And while you guys like send like the questions there, I'm just gonna show a little slide to invite you guys for our next webinar that's gonna be in February 5th, 2025. Is from Professor Juan Pablo Givaldan. He's an assistant professor of architectural engineering at Pennsylvania State University. We're gonna send an email after like this meeting, invite you guys to this presentation. You can register already. It's already open for registration. And I also wanna remind you guys about the 50 advanced in cement-based materials at University of Colorado. Please save the date, June 11 to June 13, 2025. This would be a really good conference to attend. And now I'm gonna share, stop sharing here. And let's see questions. I do have like one question. Oops. I do have like one question like for you, Chengcheng, about your first part of the presentation where you discussed about like the optimization of formulations. How you envision this like technology and this like calculation techniques in the real world? What like a lot of like concrete is as like designed and formulated in small plants or something like that. How do you envision this applying like in our current like context? I listen, you could be in the US or other countries.
So you mean your question is about how do I know like their needs, or how do...
Yeah, how do you think it does like this like technology could be applied and how do you envision that being applied today, or like how do you envision that can be transformed into what can be like useful when people are actually like either formulating a concrete or like formulating a cement in a or like calcinating cement?
Yeah, thank you for the question. I actually visited several cement plant and talked with cement engineers, cement scientists in the cement and concrete industry. I realized they are still like working a lot of repeated experimental work when they try to like optimize their material properties or when they try to decrease the carbon footprint. So that's why I search on the I do the literature review and search on the current status of the cement and concrete industry, like their practice for the optimization for the material and manufacturing. I realize it's a good way to help the industry to improve their efficiency by using this modeling and optimization, AI-based optimization work. So that's the motivation of my research. Yeah.
Sorry, thank you very much. We have one question in chat from Hito Brodo. Can this type of machine learning modeling be used over glass industry and or other optimization related problems over other industries in general?
Yes, thank you for the question. For sure, this optimization, AI-based optimization and the machine learning algorithm can be applied everywhere. As long as we have the database or as long as we have the problem statement, then we can define the objective functions like what do you want to optimize, what do you want to maximize for the glass, for example, glass industry, do you want to improve the quality of the glass, reduce the cost, reduce the carbon footprint. I can always like optimize those factors for different industries. Yeah.
Yeah, thank you very much. Also, I also have a question regarding your presentation part regarding like rheology modeling. So those models, do you like plan to, or is already like doing some like considerations regarding like the stacking of like the concrete over like the pour? Because a lot of times we can have issues with like actually like the change of the behavior due to like cement reactions and stuff like that during the using and like pumping the concrete over time, or like it can like if it was like a pre-made mix, it can be changing, or if it was like yeah, it's like changing over time. Yeah.
Yeah, thank you for the question. It's a very complicated. I know it's like for different situations, the rheology model is different. So that's the beauty of this rheology model. I can easily adjust different factors based on experiment data. I also myself, my lab, I started to work on the rheological the experiment part. So we have the rheometer, we have the viscometer. We can adjust different situations and then put those factors, put those parameters in our rheological models, like to more accurately predict those behavior. Yeah.
Yeah, thank you so much.
Thank you.
There's also like another question for Abdullah. So the cement industry and SCM, supplementary cementitious material industry, is changing every day, and that's going to impact the plastic hardening properties as well as durability of the concrete. Would you see an application of this AI model in predicting such changes and their impact?
Yes, thank you for the question, Abdullah. For sure, this application of the AI model can be used to predict those SCM industry. So like I said, the most important part is the data set. As long as we have the database, either from simulation or from experiment, I can use the AI, different machine learning, different deep learning, different optimization algorithm to train those data to predict, to do the prediction. But the data is the most important. So that's why I started to work on some experiment for myself as well to make my model more accurate for the AI training. Yeah.
Okay, so thank you so much again, Chengcheng, for this presentation. It was so interesting. We were very happy to have you here, and I think that's it.
Thank you, Allie. Thank you, everyone, for your attention. Yeah.
So, so Vicki,
Yeah.
Vicki, I think I should gonna stop recording.